So we now specifically look at the degenerate Fermi gas, and that is an ideal Fermi gas at the temperature T is equal to 0. Now the average occupation number Nk is given by 1 over Z inverse e to the power beta epsilon k minus 1, right? The average occupation number is given by Nk is equal to 1 over e to the power beta epsilon k minus mu plus 1. So now we have to figure this out at t equal to 0, but one has to be careful with this, because you see that if epsilon k is less than mu, then this term I have epsilon k minus mu is negative, so that this term is actually 1 over e to the power beta epsilon k minus mu, right? And in the limit of t to 0, or exactly at t equal to 0, beta is infinity, so that this term vanishes, and therefore you have average occupation number is equal to 1 for all energy levels epsilon k which are less than equal to mu. So similar argument, when epsilon k is greater than mu, then you see that this term is positive and the denominator itself becomes infinitely large, and therefore you get a 0. So if you want to plot the occupation number as a function of the energy level, then you will see that all the levels up to this chemical potential mu are completely filled at t equal to 0, right? And this completely filled levels define my Fermi C. So this defines my Fermi C. All energy levels up to epsilon k is equal to mu are completely filled at t equal to 0, and therefore at t equal to 0 the Fermi energy equals to the chemical potential of the system. Now since I am looking at an ideal gas where I have h square epsilon k is equal to h square k square over twice m, I can define a Fermi wave vector. Now to define the Fermi wave vector, I note that the total number of particles is sum over k average of nk, right? And the sum over k I know is gv over twice pi whole cube times 4 pi times k square dk, right? And this goes from 0 to infinity, and then I have nk, right? But nk, so the idea is to define a Fermi vector kf corresponding to this Fermi energy epsilon f, and therefore nk is 1 only up to this Fermi vector kf. So one has gv as 2 pi, this is going to be 2 pi square 0 to kf k square dk, because beyond this value of kf, the average occupation number is 0. So this quantity becomes gv over 2 pi square kf cube over 3. You immediately see that this implies that kf cube is going to be 6 pi square over g times n over v, which is 6 pi square, the number density n, divided by the g, so that kf is 6 pi square n over g raised to the power 1/3. So this defines my Fermi wave vector. And the Fermi energy, which is epsilon f, is h square kf square over twice m is given by h square twice m 6 pi square n over g raised to the power 2/3, and this is the chemical potential at 0 temperature. So let's look at the thermodynamic pressure. The thermodynamic pressure, we have been looking at this expression so many times. This was G over 2 pi whole cube, or rather, if I just take care of things, it's going to be eta is plus 1, so this is going to be G over 2 pi square integral k square dk ln 1 plus z e to the power minus beta epsilon. Now this I can manipulate and write down as integral. So let's say this is 0 to infinity, this is going to be dk. Choose this as the first function, then you have ln, there is no dk over here in the first term. When you integrate by parts, it's going to be ln 1 plus z e to the power minus beta epsilon. Of course, it's a function of k, so we can still keep that over here. K cube by 3, 0 to infinity, minus this is going to be integration 0 to infinity dk. I'll have k cube by 3, and then derivative of this log with respect to k. So that takes me 1 plus z e to the power minus beta epsilon k, and then I have z e to the power minus beta epsilon k times minus of beta del epsilon k del k. Well, it's a d epsilon k dk. D epsilon k dk, right? This term is going to vanish, so that you will be left out with g over 2 pi square. The minus and minus is going to give you a plus, the beta comes out, and you are left out with 0 to infinity dk 1 by 3 k cube, and this is z 1 by, so this is going to be k d epsilon k dk times 1 by z inverse e to the power beta epsilon k plus 1. And if you carefully look at this, then this is nothing but the average expectation value. It's nothing but the average occupation number, so that you have g beta over 2 pi square 1/3 0 to infinity dk k cube d epsilon k dk average of nk. Now the average of the occupation number at 0 temperature has the form theta of k minus kf, where theta is a Heaviside function, so that this expression is g beta 2 pi square 1/3 d epsilon k dk is going to be h square over twice m times twice k, so that I have h square over m integral 0 to kf dk k to the power 4, which is g beta over 2 pi square. I'm going to have h square over 15m times kf to the power 5. And now kf is 6 pi square n over g raised to the power 1 by 3. So that I have g beta over twice pi square 1 h bar square over 15m, and then I have 6 pi square n over g raised to the power 5 by 3. Now I also know that epsilon f is going to be h square k f square over twice m, which is going to be mu at 0 temperature. So I can equally write down twice m over h bar square half and mu to the power half. So this expression I can also write down as G beta over twice pi square h square over 15m times twice m over h bar square raised to the power 5 by 2 and mu to the power 5 by 2. So you see the beta p has this expression. Now beta beta is going to cancel out from both sides, right? What about the energy? Energy was sum over k epsilon k n k, which I know as GV over 2 pi square k square dk h square k square over twice m. So sorry, there is an average occupation over here, and nk. So this is going to be GV over 2 pi square h square over twice m, and I'm going to have kf to the power 5 over 5, right? And once again, this is going to be just GV in terms of the chemical potential. The energy is going to be twice pi square h square over twice m, and I'm going to have twice m by h bar square raised to the power 5 by 2 mu to the power 5 by 2. And there is going to be this factor is going to be 10, 5 multiplied by 2. This factor is 15 and this factor is 10, and you immediately realize that pressure is 3 by 2 times E over V, which is the usual case that for a non-relativistic gas, and which we derived very generally in our earlier classes.